This time on Battle Factory. The military menu that feeds the fight. The weapon that puts flexible firepower in the soldier's hands. And get the real feel of flying without ever leaving the ground. Battle Factory steps beyond the front lines into top secret factories where combat gear is built for battle. This packet contains enough food energy to keep a soldier fueled for the fight. The MRE, or Meal Ready to Eat, is a nutritious food ration distributed to servicemen and women in the field that can be heated on site in mere minutes. 100 years ago, dinner in the trenches of World War I wasn't as appetizing. Due to short supplies of staples and poor preservation, British troops subsisted on thin soups flavored with mystery meat, canned corned beef, and bread substitute made from dried turnips. Tins of sugary tea masked the flavor of water transported in gas tanks. Today, combat meals have been replaced by the MRE. The MRE breaks down into the flameless ration heater, the pouch of water, and the meal bag. The meals ready to eat must be prepared in a sterile environment to prevent bacterial contamination. One recipe is made at a time in an industrial kettle. First, the pre-cooked ingredients are brought to the kettle. Today on the menu, chicken with barbecue sauce, black beans, and potatoes. The preheated barbecue sauce, fortified with extra vitamins and minerals, is pumped into the kettle. Then the ingredients are poured into the sauce and mixed. Frozen chicken, dehydrated potatoes, and black beans. The MRE is health food and haute cuisine compared to the C rations of World War II. The C stands for combat, but it might as well have stood for canned. Canned meat, canned bread, and canned dessert. Affectionately known as C rats, they were only intended to feed a GI for a few days before being supplemented with real food. But toward the end of the war, C rations were all they got. By the late 1950s, the Army accumulated such a large stockpile, they were able to feed soldiers these temporary meals right through the Vietnam War. The meal bags are made from a combination of strong, flexible plastic and metal foil, making them highly durable and puncture resistant. The barbecue chicken meal is now pumped through a reservoir at the filling machine. The meal bags travel along a conveyor system where they're stamped with the ingredients, the plant number, and the date of production. Then, each bag is blown open with air jets, and the 228-gram meal is pumped into each bag. Each kettle can produce 1,400 meal bags every 20 minutes. Before being sealed, the bag is blasted with air to make sure no food is blocking the mouth of the bag. Then, the bag is heat sealed. An 8-hour shift can produce up to 100,000 meal bags. By the time the World War II C rations had arrived in Vietnam in the late 1960s, they were over 20 years old. And because the paper label often slipped off, every meal was a surprise. Today, MRE menus include Asian and Caribbean dishes, and there's even a vegetarian option. When the packages arrive at quality control, they are X-rayed for impurities, and every batch is sterilized and monitored. Samples are put into testing bags and sent through a sterilization chamber along with the rest of the batch. The monitors track the exact temperature, ensuring that the contents of the meal will be safe when reheated in the field. If a soldier gets sick to his stomach on the battlefield, he's at risk to himself and a liability to his squad. So food in the combat zone needs to be plentiful and safe. Every MRE contains 2 entrees and 2 sides, like high-energy bars and drink crystals, for a total of 1,300 calories. The packages also contain a pouch of water and 2 plastic bags called the flameless ration heaters. The bottom of the bag is a package containing magnesium mixed with metallic iron particles and table salt. Adding water causes a chemical reaction that heats it until it boils. The meal bag is inserted and left to heat, and the meal is ready to eat in 10 minutes. The final step is to seal the bags with cutlery and napkins. Then they can be packed and ready to ship to the field. War is no picnic, but if an army really does travel on its stomach, the MRE is the fuel that gets them to the front lines. Coming up on Battle Factory, a weapon with 150-meter range that doubles the fighting power. And climb aboard this craft, and you can take off without a runway or an airplane. Using the latest technology, these harmless bits of plastic will be melted and molded to create a snap-on weapon that drastically increases the firepower in a soldier's hands. The M203 grenade launcher is a single-shot launcher designed to attach under a rifle barrel. In World War I, the original grenade launchers were the infantrymen themselves, who both lit and lobbed the mini-bombs from the trenches. They could throw the grenade 15 meters fairly accurately, but would have to duck for cover to avoid the shrapnel from the explosion. The Leach Trench catapult was the first attempt at a solution, sending the grenades as far as 200 meters, but the aim was iffy. Today's version has both range and precision. The M203 grenade launcher breaks down into the barrel, the hand grip, and the receiver. The receiver of the grenade launcher is what contains the firing mechanisms, houses the barrel, and connects the launcher to the rifle. It starts off as a block of aluminum that's precision cut on a CNC, or computer-controlled machine. Once cut, the probe calculates the exact measurements to make sure that every dimension is to spec. It was originally designed to fit on the M16 rifle, but is currently compatible with many rifle models. Once the receiver is passed inspection, it's engraved with a serial number and registration code for security and quality control. Next, the receiver is anodized. The aluminum is dropped in an acid bath and charged with electricity, which alters the property of the metal surface, making it harder and rust-resistant. Once the receiver is treated, its moving parts can be added. First, the barrel latch locks the barrel and receiver together. Then the barrel stop goes in to prevent the barrel from sliding off the receiver during loading and cocking. Next comes the firing mechanism. The firing pin and cocking lever are inserted into the receiver and held in place with a locator pin. Then the safety, the trigger, and the trigger guard are installed, and the receiver is complete. World War II saw the advent of a rifle grenade that worked like a mortar and could travel 140 meters. A rod attached to the bottom of the grenade loaded into a standard rifle barrel. This crude launcher damaged the rifle and compromised its utility. Today, the modern grenade launcher doesn't damage the barrel since it's slung underneath, turning the gun into a double-duty weapon. With the hand grenade, once you remove the firing pin, you had 4 seconds to throw and run. The modern grenade launcher arms and detonates its payload differently. When the grenade is launched, the centrifugal force of the spinning missile arms the fuse. When the grenade hits the target, the firing pin is pushed back into the percussion cap, sparking an ignition, so that the grenade explodes on contact. The hand grip is a molded plastic sleeve that slides over the barrel for easy loading and protects the operator from burns. The grip is made by injection molding. Plastic granules are suctioned into the hopper, piped into the molding machine, and injected into the mold. The combination of heat and friction liquefy the plastic. Once the plastic is set, the mold opens and expels the hand grip. By the 1950s, the U.S. military had developed the M79, a purpose-built grenade launcher that looked like a shotgun with a huge barrel. These were used in Vietnam, but once the soldier was out of grenades, all he had left to defend himself was his small sidearm. So the U.S. military developed the M203 to fit on the M16 rifle. The launcher barrel is constructed of the same specially treated aluminum and is attached to the receiver. When the launcher is assembled, it gets a full function check to ensure the barrel latch and stop are doing their jobs. Finally, the receiver assembly is attached to the rifle barrel, and the M203 grenade launcher is ready to deploy. With the M203, the soldier can switch between weapons in seconds and engage targets that can't be reached by direct fire, converting a rifle from a weapon into an arsenal. Coming up on Battle Factory, the only airplane you can crash and reboot. It takes 12 months and millions of parts to create this structure that stands 9 meters high. But once inside it, you'll believe you're 9 kilometers in the air. Inside the cockpit of the CAE flight simulator, every nerve ending tells you you're flying, from the feel of the controls to the view out the window and the thrust of the G-force. In the military, by the time a pilot climbs into the cockpit of a real airplane, he's already had many hours of operational flying time without ever leaving the ground. It wasn't always this way. Prior to the advent of the flight simulator, learning to be a fighter pilot was actually more dangerous than flying combat missions. In World War I, 2 cadets were killed during training for every flyer killed in battle. Every simulator costs millions of dollars to make, but it's worth every penny. The CAE flight simulator breaks down into the motion control, the platform, the outer shell, and the flight controls. The flight control unit makes up the bottom part of the cockpit and houses the gears that control the flying movements the flight simulator makes, like thrust, pitching, and banking. The flight control unit and its many gears are milled from aluminum. The pieces are all modular and fit together like a complicated puzzle. The gears will eventually be connected to the hand levers on the control panel, the side stick, and overhead panel. They have resistance built into them to simulate the authentic feel of pilot experiences when driving the gears and controlling the aircraft. And every simulator is custom built to replicate a specific model of airplane, from civilian passenger jets to military fighter planes. The first simulator was developed by Edwin Link in the 1920s. He was an amateur flyer with a first-hand knowledge of engineering, electronics, and pneumatics from his family's pipe organ factory. He offered his Link trainer to the U.S. government in 1929, but they dismissed the concept entirely. The avionics panel contains the buttons, displays, and instrument panels that control the engines and navigation systems. Because every model of aircraft looks and flies differently, Every simulator's avionics panel is a customized copy of the airplane it's meant to replicate. 3D printers generate buttons, knobs, and handles that ensure that the simulator's interface will look, feel, and function exactly like the model of plane that the trainee pilot will fly in the real world. Over 30 kilometers of cable are cut, identified, and thread into the panel. It takes hundreds of hours to do the intricate wiring. One error would cause the aviation panel to short circuit. Next, the brains of the cockpit, the circuit boards, are assembled. A programmed robotic machine grabs the tiny circuits and drops them in the slots on the circuit boards. Then, they're passed through an oven, and the circuits are fused onto the panel. There are hundreds of printed circuit boards in every simulator, performing thousands of operations per second. Today, flight simulators are a first option for training commercial and military aviators, but they got their start on the heels of a tough and tragic lesson. In 1934, Franklin D. Roosevelt recruited the U.S. Air Force to deliver airmail across America. Flying an aircraft that had been used in World War I, the pilots were given a civilian mission very different from their wartime experience. Pilots had to contend with stormy weather and unfamiliar airstrips. In the first disastrous month of the program alone, there were 66 crashes. The nation responded to this tragedy with an outcry. Roosevelt realized something had to be done. Coming up on Battle Factory, President Roosevelt turns to an unlikely source for help. In 1934, in the first few months of delivering the mail by air, the newly commissioned U.S. Air Force pilots were crashing all over the country. In desperation, Roosevelt and the Air Force reached out to the same person that had been rejected years before, Edwin Link. 6 Link trainers were ordered immediately. By the time World War II broke, there were 10,000 flight simulators in service. The cockpit module sits on top of the flight control unit and gives the interior of the simulator the look and feel of the inside of an aircraft. Built-in speakers broadcast everything from the roar of takeoff to the thunk of landing gear being deployed. Once the module is completely outfitted, it's raised onto the carriage and secured. The rest of the interior components are installed. The panels and doors of the platform are made from heavy-duty aluminum to handle the stress of the 10,000 kilogram simulator bouncing around for the next 20 years. The sheets of metal are cut and sent to a punch press that cuts the aluminum into various shapes and then bent. Then the components are assembled, painted airplane white, and baked to a hard finish. Once finished, the platform is attached to the flight control unit and the cockpit module. The simulator is capable of its unique movement because of the design of the bearings, which act like joints. They work together to choreograph an aircraft's 3 planes of motion: pitch, front to back motion, yaw, sliding on the vertical axis, and roll, tipping from side to side. Each of the bearing houses are made from aluminum and injected with grease to keep them lubricated. Each bearing will hold a leg known as a jack at either end, which allows the flight simulator to rock and roll. The visual bowl of the simulator, which is made out of fiberglass and aluminum, stands in for the cockpit window. The ever-changing visuals are projected onto a curved mylar screen, giving the pilot in training 180 degrees of virtual landscape. In the late 1950s, simulators would use film projection of scale model terrains, and then in the 60s, advanced to TV screens outside the cockpit. By the early 70s, computers were generating crude digital skyscapes. Today, the difference between a simulated and real cockpit is virtually indistinguishable, and the sophisticated flight programs can throw any dangerous scenario at the trainee. Extreme weather, equipment failure, emergency landings, and combat scenarios. 80 years after the first mail delivery disaster, pilots are required to do hours of simulator training. So by the time they climb into the real cockpit, they won't be winging it. Because once you've flown a simulator, you're ready to take off in the real thing. While they look like simple glass tubes, they'll soon radiate enough light to tell the time in total darkness. They call it the watch that won the war. June 6, 1944, D-Day. The Allied assault on German-held Normandy was the biggest coordinated land, air, and sea invasion of all time. Over 150,000 troops had to move in perfect sync. And to succeed, every division on land, sea, and air had to synchronize their watches to 6:30 a.m. sharp. In Vietnam, night maneuvers became standard military strategy. Soldiers needed to tell time in pitch black, creating the need for the luminescent watch face. Today, the Tracer H3 watch has all the technology to keep up with the times. The Tracer watch breaks down into the face, the Tracer ring, and the capillaries. The capillaries are the watch's light source, and they begin as a 1 centimeter glass tube. They're heated and stretched until they're 0.5 millimeters in diameter. These tubes, or capillaries, are cut to 60 centimeter lengths. This military watch doesn't just glow in the dark. The tritium hands and indicators are charged by a chemical reaction that will glow day and night, 24/7, for at least 10 years. And it starts with tiny glass tubes. Next, colored phosphorus powder is poured into the tubes and then checked under black light for even distribution. Different mixes of powder generate different colors. Green is the most popular because the human eye perceives it as brightest. The capillaries now shine under black light, but in order to make them glow in the true darkness, the powder is mixed with a minute amount of radioactive gas called tritium. It's worth $30,000 a gram. First, the tubes are attached to a device that will distribute the tritium. The glass tubes are flash frozen in order to better trap the gas. Then, tritium gas is pumped into the frozen capillaries and then heated to mix evenly with the phosphorus powder. A chemical reaction between the tritium and the phosphorus is what gives the tubes their luminescence. Then, the ends are pinched and sealed shut. The radioactive tritium is now encapsulated in the glass, making it completely risk-free for the wearer. Next, the tubes are laser cut into small pieces that will fit easily onto the watch face. The tiny light-filled capsules are checked under a microscope for size, shape, and glow factor. A robotic arm then lines up the pieces perfectly onto pallets in preparation for assembly onto the watch face. Assembling the watch face starts by adding capillaries to what is called a tracer ring, a ring which displays every hour. A robotic arm drops a glowing capillary into the hour indicators. Next, a capillary is added to each of the watch's hands. Then, the watch face and the tracer ring are pressed together. The watch hands are then carefully attached, and the outer case is mounted on top of the face and tracer ring. Finally, the back plate is pressed on and squeezed shut. The completed watch is then labeled with laser engraving. The Tracer H3 isn't just a pretty face. It's got to be deadly accurate under the most rigorous conditions. So the watch is dipped in a solution of salt water that's the same concentration as human sweat. It gets punched in the face, dropped on the ground, blasted with extreme temperatures, and shaken up to make sure nothing comes loose. If it's rugged enough to survive the test, a band is strapped on, the watch is tagged, and the Tracer is good to go. On the battlefield where every second counts, keeping time means staying alive. Coming up on Battle Factory, a first response tool that cuts out a path to safety. And a complete overhaul puts this battle tank back in the battle. Each one of these handcrafted precision-cut pieces will come together to create a first response tool capable of chewing through metal like a can opener. At the scene of an accident, a natural disaster, or in the combat zone, the jaws of life can cut through just about anything to gain access to a victim and pluck them from the jaws of death. Prior to the 1970s, rescue efforts were performed using crowbars, winches, and circular saws, which had the potential to send sparks flying into gas-filled wrecks. In addition, they all needed power from an external source. Today, the Jaws of Life spreaders and cutters are handheld and battery-operated and weigh under 23 kilos. The Jaws of Life cutter breaks down into the cutter, the pump body, and the cylinder. The cylinder starts as a length of solid aluminum, which is cut down to 45 centimeters. Then, the ends are ground to smooth out any sharp edges. The cylinder is placed inside an automated lathe. First, the end is turned and threaded. Then, the center is bored out. Next, the cylinder is secured in a computer-controlled cutting machine. While the metal is showered with jets of anti-friction liquid, sections for the center are milled out, and the area where the cutter will attach is carved. The same process is repeated to produce the piston, which moves the heavy cutting blades or jaw. The pistons move in and out of the cylinder under hydraulic pressure to open and close the jaws. The piston is fitted with O-rings, then lubricated so it can slide into the cylinder without damaging the interior. On September 12, 2001, one day after the tragic attacks on the Trade Center in New York, 2 Marines sifted through the rubble at Ground Zero, and they heard cries for help. Using the Jaws of Life, rescuers were able to cut through concrete and metal girders and reach 2 Port Authority cops who were buried 30 feet under the concourse and pull them out alive. Next come the cutter blades, which act more like a nutcracker than a pair of scissors. In fact, the blades only make a small initial cut into the metal. Then the sheer force of the jaws actually fracture it like a stone. And they have a force that can crack through almost 4 centimeters of solid steel. Special heat-treated metal is used to ensure that the blades are tough enough to chew through concrete, steel, and brick. Next, A steel pivot pin secures the blades together, and a lock nut fastens them tight. Finally, flexible rubber guards called blade boots keep the sharp end of the tool away from the operator's hands so it can be used safely. The jaws of life are powered by a hydraulic pump, which is housed in the pump body. The pump body is fitted with an electric motor and a bladder filled with a liter of hydraulic oil. The incredible force of the cutters is achieved by pumping fluid under very high pressure into the cylinder. The fluid forces the piston up and opens the arms of the cutter. The operator can then toggle the switch the other way and cause the piston to retract, which closes the arms. The engine runs on a battery, which is powerful enough to make 40 cuts without replacement. The pump engine is screwed onto the end of the cylinder, which is then covered in a protective plastic case. Before they can be put into the field, the jaws of life undergo a series of tests. The first test measures the jaw's power by biting down hard on a pressure-sensitive gauge. If the jaws don't bite down hard enough, it doesn't leave the plant. Next, the hydraulic pump is tested for leaks. Once it's field ready, final touches are added and it's packed up and shipped out. The jaws of life's next assignment could be a car crash or rock slide, a smoke-filled Humvee, or a building toppled by enemy mortar fire. And it may have to cut through twisted metal or concrete walls. But the goal is always the same: get rescuers in and victims out alive. Coming up on Battle Factory, an overhaul puts this tank back in fighting shape. This tank is in for an overhaul, and it's going to take 1,600 man-hours, several months, and $1 million to get this battle tank back into fighting form. And it's worth every penny. On February 24th, 1991, at the height of the Gulf War, U.S. tanks and armored vehicles raced east from Saudi Arabia into Iraq in a daring flank maneuver, later nicknamed the Hail Mary. The armored vehicle that would lead the attack was the coalition force's heavy hitter, the M1 Abrams tank. The M1 Abrams tank is the U.S. military's top gun. Since it rolled onto the battlefields in 1991, it's been the toughest, fastest, and smartest fighting machine on the ground. After 5 to 10 years of service, these $8 million tanks get battle-weary, and it's cheaper to refurbish them than to purchase new ones. And kitted with current technology and innovative add-ons, these rebuilt M1s will be better than new. The M1 Abrams breaks down into the turret, the engine, and the hull. Weighing in at 62 tons, each tank is shipped in by rail and lifted off the track by a 40-meter-high crane. It's towed into the factory, and deconstruction can begin. First, the turret is uncorked from the hull and hoisted onto a transport dolly. It will take 4 months alone to dismantle the tank down to its 12,000 parts. Some parts will be tossed, some will be refurbished, and some will be replaced with better quality components. The complete overhaul will take 10 months. Next, the 2,300-kilogram tank tracks are removed, rolled, and carried off on a forklift. The wheels and suspension are stripped off, leaving the empty 37-ton hull. The hull is armored with a composite of ceramic and spent plutonium that can withstand the enemy's best shot in a tank battle. The Abrams can dish it out, and it can take it. The hull is lifted onto a large dolly. which transports it to a massive bay called a spinner hangar. Then the crane moves the hull into a vertical position. Next, it's placed safely behind 10-meter-high, 7-ton doors. Inside, millions of tiny steel pellets are blasted at the rotating tank hull, stripping away old paint and corrosion. In 90 minutes, the hull surface has been scraped back to its original metal. Next, certain spots on the hull are cut so the tank can be retrofitted with upgraded computer and weapon systems. Next, it's primed and painted with a durable military-grade paint, giving the tank another layer against the elements. The M1 Abrams' unique engine and transmission are called the Power Pack. It combines a 1,500 horsepower turbojet engine with a 6-speed hydrokinetic transmission. The tank can accelerate from 0 to 30 kilometers per hour in 7 seconds and travel at speeds of up to 70 kilometers per hour. The Abrams engine is versatile and will run on just about anything that will burn, including gasoline, jet fuel, and even perfume. The engine and transmission take 4 weeks to overhaul. When they return from battle, they're coated with dirt and riddled with rust. Sand is the nemesis of the Power Pack, and in current theaters of operation, sand is everywhere. In February 1991, in the thick of Desert Storm, a squadron of American M1 Abrams battle tanks rolled towards Iraq. The mission? Cut off the Iraqi threat to Kuwait and take down the Republican Guard divisions near the Iraq-Kuwait border. The Americans were hoping for a surprise attack, but they were spotted. A squadron of hundreds of Iraqi tanks manned by the elite Republican Guards geared up for what was to be a classic standoff. Coming up on Battle Factory, the M1 Abrams turns a blinding storm into a Hail Mary maneuver. In the early hours of February 26, 1991, American forces were headed for a face-off against the tank units of the Iraq Elite Republican Guard. The outcome of the skirmish would play a deciding role in the success of the Iraq War. The Americans' offensive line was led by 36 M1 Abrams. They had hoped to have the advantage of surprise, but a slow advance gave away their position. Then, a sandstorm swept through the desert, cutting off their air support and reducing visibility to 0. They were on their own, outgunned, and heading into battle. After 8 months of the rebuild, the M1 Abrams is ready to be put back together. Its hull has been stripped, it's been repainted, outfitted with armor, and the engines have been rebuilt. All of the tank's parts have been either retooled or replaced. It's time to reassemble the 68-ton giant. Then, the tracks are laid out. A drag line pulls the tracks over, and they're wound onto the sprockets and road wheels. Then, connectors are hammered in to hold the tracks in place. The turret fits back onto the hull like a 21-ton cap into the refurbished ring. It's a tough, delicate operation, lowering the heavyweight turret and a 6-meter cannon until it's perfectly aligned. In a blinding sandstorm, U.S. forces found themselves up against an unseen enemy. But the M1 Abrams could turn this desert storm to their advantage. Equipped with revolutionary GPS systems, they were able to navigate through 0 visibility and pull a Hail Mary flank move to sweep around the Iraqis, who they'd ID'd with thermal imaging. And when the sand cleared, the Americans were right on top of the Republican Guard. They didn't stand a chance. Before returning to the battlefield, the M1 Abrams has to survive the proving ground. a series of rigorous tests designed to push the tank to its limits and assess every aspect of the rebuild. Failure here could mean casualties in the combat zone. The tank tears through its paces, testing speed, target lock, and turret rotation, mobility, and sharp angle climbs. The M1 Abrams is battle ready. After 10 months, the refurbished tank is better than before, maybe even better than when it came off the line the first time around. The U.S. Army plans to keep on refurbishing this model until 2040. By then, there will be M1 Abrams that have served 50 years of active duty, that are veterans of the last great tank battle of the 20th century. This chunk of carbon steel will be honed and hammered into a military icon that's as old as war itself. Used as the primary weapon in battle for over 5,000 years, over time, the sword became lighter, sharper, and even more deadly. However, by World War I, fighting style had changed. Hand-to-hand combat was replaced by trench warfare and the machine gun. The sword saw little action. But 100 years later, it still performs a ceremonial role, symbolizing rank, courage, and honor. Today, every British soldier who achieves the rank of officer has the privilege of wearing a sword. This workshop south of London is one of the last where cavalry swords are handcrafted individually, using techniques that are centuries old. Designed in 1912, the cavalry sword breaks down into the handle, the guard, and the blade. The blade begins as a billet of raw carbon steel. Carbon has been used in making swords for over 1,000 years. It's ground into its basic shape and dipped into oil. Then a groove called a fuller is ground into the flat side of the blade. Also known as a blood groove, the fuller is designed to make the sword lighter and easier to pull out of the target. The blade is baked in an oven to harden the steel. Then it's cooled or quenched in oil. The hardening process sometimes causes warping, so in order to straighten it, it is first heated with a blowtorch. Using a press that looks like it hasn't changed much in centuries, the warps are pounded out of the blade. Then the bladesmith finishes the straightening with a hammer and an experienced eye. The blade is then tested to make sure it's flexible enough to bend without breaking. And it's struck against a rounded metal surface to make sure it can take the impact without cracking. Finally, the blade is polished to a high mirror finish. While the cavalry sword was obsolete by World War II, one eccentric soldier, British Lieutenant Colonel John Churchill, maintained that any officer going into battle without a sword was improperly dressed, and he became known for charging into battle wielding his sword. His nickname became Mad Jack. Etching swords is an art that's been practiced without much change since the Middle Ages. Thick red paint fills the patterns in a steel mold. Then it's transferred onto paper. This cavalry sword is marked with a decorative pattern and the royal cipher. The ER2 stands for Queen Elizabeth II. The paper is gently rubbed onto the blade and peeled off, leaving behind the painted pattern. Then the blade is dipped into an acid bath for 20 minutes. The paint is acid resistant, so when the sword is removed and rinsed, the paint is scraped off, leaving the ornate pattern etched in the blade. This technique has been used for hundreds of years. The cavalry sword has an ornate guard that was originally designed to protect the swordsman's hand. Its basic shape is traced onto a metal sheet and cut. Then, the pattern is silk screened on with paint and dipped in acid. Once the pattern has been etched on, the guard is pounded into shape on a press, then hammered home by hand. The traditional wood handle is wrapped tightly in actual stingray skin, a unique leather that's been used for centuries. Once it's glued and dried, the skin is painted. Finally, silver wire is wound into the handle's grooves to give it a good, solid grip. Mad Jack, the last soldier to carry a sword in World War II, was ordered in September of 1943 to capture a strategic German-held post in Salerno, Italy. Hopelessly outmanned, Churchill crept through the base, swooping in on unsuspecting soldiers and drawing his sword. Mad Jack captured 42 Nazi soldiers, took the German post, and earned himself a Distinguished Service Order. Once all the components have been created, the blade is locked onto a table vise and the sword is assembled. The guard and grip are slipped onto the blade and bolted on tight. Then the pommel, an ornate cap, completes the sword. The sword hasn't been relied upon in combat since the exploits of Mad Jack Churchill, but it will forever remain a part of military dress and military history. Coming up on Battle Factory, this bullet won't kill you, but it will make you stronger. And a scrappy little dogfighter that's been Top Gun for 40 years. These aluminum rods and plastic pellets will be molded and machined into simulated ammo that fires like the real thing. When it comes to training options, this is number one with a bullet. Urban warfare is a harsh reality of today's military theater. Adrenaline-fueled operations that take the soldier directly into the enemy's house, facing attack from behind doors and around corners. By late in World War II, Allied troops needed to train for urban warfare in a real-world setting. So, residents of the English village of Imber were asked to leave their homes so U.S. troops could train for D-Day on their streets and in their houses. In close-quarter combat, panic, fear, and blind aggression are inevitable. And the closer the soldier can get to the real thing, the more effective the training will be, right down to taking a bullet. Simulated ammunition is a cross between a bullet and a paintball. It fires like real ammo, it hurts, it leaves a mark, and it lets soldiers know with dead certainty if they've hit their target or become one. The man marker simulated ammunition breaks down into the components, the cruciform dome, and the slide. Made from rods of aluminum, the slide will house the component parts of the simulated slug. The rods are dropped onto a conveyor belt and turned on an automated multi-spindle lathe, which spits out 50 finished slides per minute. Every slide passes through a high-speed sensor, which analyzes it for quality and measurement. If it detects the tiniest speck of debris, or if the size is off by even 0.001%, the entire batch is rejected. Then the slides are laser engraved with the production date. The plastic cruciform dome is the outer casing of the bullet. First, plastic pellets are put into a dryer. Then, they're molded to form the little plastic domes that make up the tip of the simulated ammo. This process outputs 500,000 domes every 24 hours. Once the components are completed, they're conveyed to a robotic assembly line. Each of the bullet's 10 parts is dropped into individual hoppers and then fed into the machine. The slide is inserted with the projectile charge, a firing pin ball, and the rear power load. Then, an inertia applicator ball is installed along with the marking compound that leaves its telltale spot on the target. Finally, the plastic cruciform dome is capped on top. They may be simulated, but these bullets are fired from real guns so that soldiers can train on the same weapons they'll be carrying into combat. After installing a conversion kit into the rifle's action, the magazine, loaded with simulated bullets, is ready for testing on live targets. The training ground is laid out for fishing, short form for fighting in someone's house. A firefight with simulated ammo gets the soldier used to being shot at. The projectiles break upon impact and leave a mark. And there's no mistaking the feedback. A red dot on your chest means you've been hit. In 2013, the U.S. Army built a 300-acre city to use as a facility for urban warfare and house-to-house confrontations. Simulated ammunition plays a critical role in these scenarios, and the way a soldier reacts to a simulated firefight could make the difference between walking out of that house and getting carried out. Coming up on Battle Factory. Whatever the mission, this lightweight skyfighter earns its wings. Brainpower and firepower transform 8,000 kilograms of computer-controlled machinery into a legendary dogfighter with the best fight and flight record in the sky. The F-16, known as the Fighting Falcon, is equally effective in air-to-air combat and air-to-ground attack. And at Mach 2, if you hear the F-16 coming, it's already too late. During the Vietnam War, the United States sustained dramatic losses. The F-4 Phantoms often struggled to take down the supposedly weaker Soviet MiG-21s at close range. So a maverick group of engineers known as the Fighter Mafia was determined to design a lightweight maneuverable jet that could handle both air-to-air and air-to-ground operations. And in 1974, they pulled it off. 40 years later, the modern version of the fighter jet is still almost identical in shape and size. The secret to its agility and speed is a sleek, compact fuselage. The F-16 breaks down into the aft, the center and wings, and the forward. The forward fuselage is the nerve center of the airplane and takes over 9 months to build. It houses the cockpit, gun trough, fuel tank, and the piloting and navigation systems that were a true innovation when the F-16 first took to the air. The forward fuselage starts as an aluminum shell. In the electrical harnessing station, over 70 kilometers of wire are strung through the fuselage, connecting the cockpit controls to navigational and weapon systems. Each wire is hung before install to allow it to stretch. A wire that shrinks or recoils mid-flight could be catastrophic. The F-16 is a fly-by-wire aircraft, which means that the pilot's commands are relayed electronically instead of employing the hydraulics. This decreases the number of moving parts, making the plane lighter and safer. When it was first introduced in 1974, pilots needed to get used to the feel of what they dubbed the electric jet. Once the wiring is complete, the forward is transferred across the factory to a test bay where every electronic and computer component will be analyzed to make sure the fly-by-wire system is functioning perfectly. Every control panel component is tested, from radar display to the targeting and navigational systems. They test the heads-up display, which projects navigational data and weapon status right onto the canopy glass. A real-world computer interface that shows the pilot where he is and where to target his missiles. Then the bubble canopy is attached and tested. It's made of high-strength polycarbonate that gives the pilot a 360-degree view. Finally, the forward is hoisted over to the flatbed and put aside for the mating process, where it will be joined to the center and aft sections of the plane. Since the 70s, the F-16 has always been known as the Fighting Falcon, but its sleek, compact forward fuselage earned the plane a new nickname, the Viper. Because of daring missions like in May of 2011 involving aggressive diving, quick strafing fire, and deadly use of missiles, the bird became a snake. The center fuselage houses the landing gear, the in-flight refueling system, and the wings. The center starts as a barrel shape. Panels are screwed onto the frame to keep the structure together. Next, bulkheads that act like ribbing are built around the barrel. These will allow room to house the fueling system, the electrical wiring, and make space to attach the landing gear. A metal skin is attached to the outside of the structure. The aluminum skin is made to be subjected to the extreme temperatures and stress caused by flying at supersonic speeds and at altitudes up to 15 kilometers in the air. Once complete, it's set aside to wait for mating. The aft fuselage houses the exhaust port and the small fins and wings that help to steer and stabilize the plane. Once all the pieces of the fuselage are completed, they're transported to another hangar to be assembled. On a mission in Afghanistan, high above the desert floor, F-16 pilot Major John Caldwell spotted a small unit of U.S. and coalition special forces being ambushed by almost 100 Afghan insurgents. He decided to take them on. He armed his F-16's Gatling gun and braced himself for the fight of his life. Coming up on Battle Factory, the F-16's exploits earned the Fighting Falcon its nickname. While on a routine patrol, F-16 pilot Major John Caldwell caught an ambush in progress. A small Special Forces team had been attacked by an insurgent cell and were fighting for their lives. Caldwell swooped in and laid down strafing fire with his aircraft's 20mm gun to create distance between the insurgents and Special Forces squad. Then he pulled his aircraft up, came back around, and dropped a satellite-guided bomb on the attackers, neutralizing the ambush. Caldwell was awarded a Distinguished Flying Cross. The Fighting Falcon lives up to its nickname, the Viper. In the mating station, the completed pieces of the aircraft's fuselage are dropped into a fixture to be joined together. It's a precise and painstaking operation. Next, the tricycle landing gear and vertical stabilizers are installed. The fuselage is hoisted onto a ceiling-mounted crane, and the horizontal stabilizers and wings are installed. The radome, or nose of the aircraft, houses the F-16's state-of-the-art radar system, which detects standard environmental elements like wind and airspeed. The F-16 is powered by a turbofan engine, which can accelerate the aircraft to more than twice the speed of sound, or over 2,200 kilometers per hour. The F-16's smart, modular design means that the engine can be removed, serviced, and replaced easily in any airfield in the world. Once it's assembled, the F-16 is transported to an environmentally controlled paint hangar. The temperature is kept at exactly 23.9 degrees Celsius, and the air is filtered of debris, which can cause millions of dollars worth of engine damage. The classified paint formula contains rubber, which masks the aircraft's heat signature and reduces radar detection. Once it's painted, the F-16 is ready to hit the runway and take to the air. Since its initial production in the 1970s, over 4,500 F-16s have been produced for 28 different nations. For 40 years, the Skyscraper has proven to be the best fighter in and beyond its weight class, defending its reputation as the dogfighter that does it all. The F-16 is never coming down. These dull gray steel rods and plain metal plates will be machined into a deadly arms weapon that's been the U.S. military's go-to big gun for almost 100 years. The M2 machine gun is a 50 caliber belt-fed air-cooled heavy machine gun that's considered one of the most effective and destructive weapons of all time. The first gun capable of firing continuous rounds was the Gatling gun, invented in 1862 by Richard Gatling and employed by the Union Army during the Civil War. It was a rapid-fire machine gun, but still needed a person to hand-crank the barrels. By World War I, machine guns made use of the bullet's recoil force to reload the next bullet and became the first truly automatic weapon. The M2 was first designed by legendary gunmaker John Browning at the end of World War I and has since been in production longer than any other machine gun. Today, the M2 machine gun is even used as a heavy weapon mounted on board armored vehicles and battleships, and is still the top choice for anti-aircraft and infantry support. The M2 breaks down into the receiver and the barrel. The barrel of the M2 starts as a 1 meter long blank made of cryo-treated weapons-grade steel, which means it's been cooled to minus 185 degrees Celsius to harden and strengthen the metal. It is tough enough to handle 600 rounds of ammo per minute and is tested to well over 15,000 rounds. First, the barrel blanks are heated in an oven to keep the barrel from warping during machining. Then, the blanks are mounted on a lathe where the center of the barrel is bored out. A drill bit creates the initial hole in the center of the barrel, which is then widened and honed. Once complete, the barrel is ready to be rifled. Rifling is a process that etches grooves into the interior walls that cause the bullet to spin as it flies, which improves aim and accuracy. While the barrel rotates counterclockwise, a drill bit turns clockwise to rifle the inside, creating helical grooves on the interior walls. When the bullet leaves the barrel, it'll be traveling at 840 meters per second. Next, a lathe scrapes off additional debris from the outside of the barrel. Once the barrel is complete, the work starts on the receiver. The M2's receiver is the part of the gun that makes it an automatic weapon. It houses all the operating parts, and it's built to receive the ammunition belt, and it can fire 10 rounds every second. The M2 is a recoil-operated machine gun, which means that the energy provided by the recoil powers the loading of the next round. Used cartridges are rejected from the bottom of the gun. Side plates make up the outer walls of the M2's receiver. The plates are magnetically held in place and then cut on a computer-controlled cutting machine. The feed bracket, which feeds the belt and ammo into the receiver, is installed on the right side plate. Next, an orbital riveter rounds out the metal to secure the rivets. It is so powerful that it can manipulate the tough metal as easily as if it were clay. Heat is used to expand the rivets for a tight fit. Then the excess material is ground away. Next, the top plate is installed, followed by the bottom plate and the breech assembly. The M2 can be set up to fire a single shot for pinpoint accuracy up to 2,000 meters away, and then switch easily back over to sustained automatic firing mode, firing for as long as the trigger is held. The M2 hasn't changed much in the last century since Browning first designed it. In January 1945, in the north of France, the M2 lived up to its full potential. An American infantry company led by Lieutenant Audie Murphy was attacked by a German tank unit. Murphy ordered his men to scatter into nearby woods. He got behind his M2 machine gun to take on an entire German tank platoon. After an hour, the brave soldier and his machine gun held off 6 advancing heavy tanks. He foiled the counterattack and secured the American key position. After the war, Audie Murphy's art reflected his life. He starred in countless adventure films, many of them World War II movies. Murphy went from a machine gun-wielding hero to an icon of the silver screen. Next, the assembled receiver is sandblasted to scrape off a thin layer of steel. This is in preparation for exposing the receiver to chemical baths. First, the receiver is dipped in a chemical bath that makes it rust-resistant. Then, it's neutralized in a water bath, and finally coated with chrome sealant. Then, the receiver is baked in an oven for 4 hours at 80 degrees Celsius to dry out every crack and crevice and prevent the internal rusting that could weaken the gun. Now, the M2 is ready for assembly. The barrel support is attached with holes that help vent the heat created by semi-automatic fire. Then the final attachments are added, and it's ready for testing. Once the M2 is built, it's taken out to the firing range. 100 rounds are cycled through it so that every moving part is tested for functionality and accuracy. Once the M2 is ready, it's sent out for active duty. Coming up on Battle Factory, camouflage cover-up that really covers up. And the driving, climbing, go-anywhere amphibian. They're just globs of color now, but when applied to a soldier's face, they could paint him right out of the picture and maybe save his life. Camouflage makeup is designed to make a soldier disappear. This military-grade compound is a long way from department store concealer. It's sweat-proof, infrared-resistant, and stays on in a drenching downpour. In the early 20th century, combat became more covert. And by World War II, soldiers were applying camouflage makeup to hide in plain sight. In the jungles of Vietnam, Navy SEALs always wore makeup during their operations and became known to the Vietnamese as the men with green faces. Camo makeup breaks down into the case and 3 different shades of paint. The base of the camo paint is solidified vegetable oil. It's basically the same stuff you'd use to make French fries. It's sectioned out into blocks in preparation for heating and set aside. Then, colored powder is measured out. The pigments are shades of green and brown that can be adjusted for jungle operations and nighttime raids. The secret anti-infrared ingredient makes the wearer less visible to thermal imaging scopes. Exposed skin reflects light and attracts attention, so camouflage is often applied in 2 colors in an irregular pattern. Shiny areas are painted with a dark color, and shadow areas are colored with a light color. Next, a polysorbate is weighed out. This emulsifier allows the ingredients to bind together. It also makes the paint creamy, so it's easy to apply and remove. A preservative ensures that the paint won't spoil in the field. Finally, a thickener is added to make the paint sweat-proof. Then the ingredients are blended together. Each color has its own mixing vat. Like a chef's recipe, the ingredients are added in a prescribed order, starting with the vegetable oil bricks. First, the oil bricks are heated to 90 degrees Celsius to melt them into a thick fluid. Then, the powdered pigment is poured in, followed by the rest of the ingredients. The concoction is mixed for 2 hours until the blend is smooth and creamy. When the paint is complete, it will not only be long-lasting and sweat-proof, but perfectly safe to wear. In the days before the D-Day invasion of Normandy, a legendary paratrooper unit were the first soldiers known to use camo paint. Not as camouflage, but to strike fear into the hearts of the enemy. The demolition squad shaved their heads down to mohawks, covered their faces in war paint, and earned the nickname, the Filthy 13, when they refused to wash their uniforms until victory was theirs. Their daring exploits were mythologized in the 60s war movie, The Dirty Dozen. Once the paint is ready, mirrored cases are placed on a rotating carousel. Each of the 3 colors is injected into a separate compartment. The case is then fed down the line onto a vibrating conveyor. The vibrations settle the paint into its compartments. Each compact is then tapped to settle the paint further, check for flaws, and sent to packaging. Every compact is labeled with the ingredients and expiry date. Then they're boxed for shipping to soldiers in the field. In the combat zone, soldiers will often work in pairs to apply the camo paint. Soldiers, especially special ops and snipers, wear camouflage uniforms to blend into the background. Camo paint completes their covert coverage, so they can get to their target before they become one. Coming up on Battle Factory, wheels turn to paddles when this road warrior hits the surf. Once these 8 wheels are locked on, this all-terrain vehicle won't just roll, it'll swim. The Argo Amphibious ATV is a nimble personnel carrier that can handle rocky roads or muddy swamps, plunging into rushing rivers and paddling through deep water. Light enough to drop out of a helicopter, the Argo is the go-to ATV for special ops units, border patrollers, and first responders. Amphibious vehicles were first developed for the military in the years leading up to World War II. They combined elements of cars and boats to access places that neither alone could get to. By 1944, when the Allied forces stormed the beaches of Normandy, larger amphibious vehicles were a critical part of the arsenal. Today, the lightweight and versatile Argo is the evolution of these first-generation amphibians. The Argo breaks down into the engine, the transmission, the wheels, and the body. Part of what makes the Argo amphibious is its lightweight, waterproof body. Unlike a car, The ATV's outer body is made of 2 pieces of polyethylene joined together in a watertight seal. In a large thermal forming machine, a sheet of specially designed plastic is heated to 177 degrees Celsius for about 20 minutes. The machine inflates the softened poly, forming a kind of plastic balloon. As it rises, the metal die rises up against the plastic surface, and the air is sucked back into the machine. This negative pressure molds the plastic against the die to form the shape of the ATV's upper section. Once it's cooled and hardened, a tech drops a jig onto the molded plastic. The jig lines up with the body shape and guides where to punch out holes for wiring and throttle controls. Then, the engine hood and waterproof battery compartment are removed from the mold and trimmed of excess plastic. The bottom half of the body looks and performs like the hull of a boat. Holes are routed for axles and water drainage. The next step is to make the chassis. The lightweight frame of the ATV is made of high tensile strength steel alloy, cut and welded into shape, which will support the body, the engine, and suspension system. Then, the chassis is set aside until assembly. The key to Argo's Go Anywhere capability is its state-of-the-art Admiral transmission system. Almost 40 different gears will go into this revolutionary transmission, fully engineered and manufactured on-site. The gears are constructed on a computer-controlled machine that cuts each gear out of high-strength steel alloy. Jets of coolant keep temperature and friction down. When a gear is finished, an automated rotary arm extracts it from the machine and picks up another piece of steel for milling. The Admiral 8-wheel drive transmission means every wheel is getting power from the engine simultaneously and rolling independently. This gives the Argo incredible mobility. It can pull 360 turns with ease and ride over just about any surface. After the ATV played a critical role on the beaches of Normandy, it would help to make inroads in the liberation of German-occupied Europe. In 1945, as the Nazis were retreating through Holland, they flooded the landscape to try and bog their Allied pursuers in the mud. In their attempt to escape capture, they also put the occupied Dutch beyond help. If the Allied forces couldn't traverse the terrain to reach the Dutch people in time, it wasn't just delaying their liberation. It also meant death by starvation. Coming up on Battle Factory, the Allies send help by getting on board a buffalo. In the final days of World War II, the German army was on the run in what was once occupied Holland. They tried to create distance between them and their Allied pursuers by flooding the landscape, which stranded the starving Dutch citizens. But the amphibious vehicle of the day, the Buffalo, was able to get troops and supplies through the water and over the mud. The amphibious vehicle foiled the Germans' plans and became instrumental in the liberation of Holland. Once construction of the Argo amphibious vehicle is complete, components are assembled. First, the transmission is dropped into the chassis and secured. Then, the chassis is lowered into the bottom section of the molded body. The transmission and drive chains are cabled and connected. The frame is secured, and the engine, mechanics, and electronics are installed. A self-adhesive waterproof gasket is applied to the edges of the bottom section of the body. The upper body is lowered onto the bottom, and the sections are clamped together to make sure the watertight adhesive bonds. The two halves of the ATV are riveted together to keep it watertight. With the body complete, The wheel assemblies are bolted in. Gaskets surround the axles to keep the water out. The tires have a raised tread, enabling the Argo to swim in deep water. When the wheels spin in the water, it acts like a paddle so that the Argo is propelled forward. Rough edges are trimmed of excess plastic. Dust is blown clear, and the ATV gets a function check. The battery is sparked, and the engine gets a good rev to make sure the Argo is alive and kicking. Now that it's field ready, the Argo is put to the test. The Argo tears through the course, swimming through deep water and skimming over rough terrain. Steep curves and sharp turns are child's play for this agile ATV. But on military assignments around the world, the Argo is all business. This aluminum block will soon hold a piece of ground glass that has the power to extend a sharpshooter's eye, so he can see, stalk, and connect with a target that's kilometers away. The Riflescope is small, lightweight, and has a revolutionary fog-proof lens, so the glass will not fog up no matter what the weather. The sophisticated Riflescope began in the 17th century as a set of crosshairs, actually made from human hair or spider webbing, and mounted on the tip of a rifle barrel. But today, with advances in rifle and scope technology, elite snipers have made record shots at seemingly impossible distances, up to 2.5 kilometers from their target. The loopholed Riflescope breaks down into the lenses, the erector system, and the main body. The body starts as 3.7 meters of aluminum tubing. The blanks are placed in a computer-controlled cutting machine, where they rotate on a spindle. First, the eyepiece end is cut. Then, the objective end, the side that faces the target, is machined. Riflescopes have 3 main sections that magnify an image: the objective lens, the internal erector lenses, and the ocular lens. As the light passes through the series of lenses, the image starts upside down and is then flipped back before being magnified. Next, the erector system of the scope is machined. The pivot tube, which will hold the internal lenses, and the cam tube, which slides over top and controls the movement of the lenses back and forth. Next, the eye shell and lens holder is machined and washed. Finally, mounting rings are cut. These will fasten the scope to the rifle barrel. The rings are then stamped with a logo and set aside for coating. Next, it's sandblasted to prep the body to be anodized, a chemical treatment that coats and protects the aluminum. During the Vietnam War, the legendary American sharpshooter, Carlos Whitefeather Hathcock, became one of the Viet Cong's most feared snipers. An equally lethal Vietnamese sniper known as the Cobra was enlisted to take him out. Meanwhile, Hathcock was tracking the Cobra. While stalking his adversary, Hathcock caught a momentary glint in the undergrowth and fired at the reflection. He sent a bullet directly through his enemy's scope, killing the Cobra. Later, Hathcock realized the only way he could have made the shot was if he and the Cobra had been looking directly through their scopes at each other at the exact same moment. Lucky for him, Hathcock fired first. After being anodized, the scope is now a matte black. All the anodized parts are placed in a carrier basket and ferried through a series of tanks containing detergents and cleansers that prep them for a 100% sterile environment. In a clean room, the eyepiece is assembled. Then, the rings are glued together and the ocular lens is dropped onto the eyepiece. Then, the erector system is assembled and the main tube is put together. Once the scope is fully assembled, it is calibrated to make sure the optics and mechanics line up perfectly. When a sniper is taking aim, he may not be putting his target in the crosshairs, but adjusting his scope to compensate for distance, temperature, and wind velocity. The scopes are then inserted onto blocks, and a tiny piston shoots inert gas into the main tube. This will prevent fogging in the field no matter what the temperature or humidity. Then the scopes are fitted onto a carousel and put through the dunk test. If any bubbles are visible, that means there's a leak. Finally, the adjuster tubes are added for wind variation, elevation, and focus. The scope sits securely on the rifle barrel. The shooter squints through it, putting his target in the crosshairs, making minuscule adjustments. This refined melding of precision optics and crafted mechanics all come down to one moment and one shot. Coming up on Battle Factory, the airborne care package that can find its own way to the drop zone, and military footwear from boot camp to the battlefield. When they're packed up, these containers will be giant care packages, bringing airborne aid that can make the difference between help and being helplessly stranded. And not only can they fly, they can get there on their own. Precision Aerial Delivery System, or PADS, are guided by GPS. Computer coordinates program the airdrop, and built-in motors using pulley systems steer the package for up to 15 kilometers, transporting loads of supplies and landing within 100 meters of the drop zone. While the military had been dropping bombs out of the sky since World War I, it was only in the Second World War that they began using their planes to airdrop food, medicine, or weapons to soldiers operating deep behind enemy lines. But these airdrops were hit and miss. Packages often landed kilometers away from their targets. Today, NATO considers precision airdrops among its top priorities for humanitarian aid and defense against terrorism. The Sherpa model breaks down into the parachute, the payload, and the guidance unit. The black box, called the Aerial Guidance Unit, consists of two small metal compartments that fit together. The first step is to assemble the upper half, or the muscle of the guidance unit, which contains the basic driving mechanisms and pulley system. The pulley system will tug on the parafoil's lines to steer the Sherpa to its drop zone. The lower half is the brains of the unit. It houses the GPS software that can track where it is and where it's headed. A stack of computer cards receives location information from the GPS receiver. It computes a flight path to the target point and instructs the parachute when to open. The onboard receiver means that the unit can also be controlled using a remote control. A battery is installed and the two halves are assembled. Now, the aerial guidance unit is ready for rigorous testing. If the drop is from 9 kilometers over the desert, the temperature starts at a freezing 50 below, then soars to plus 40 as it lands on the burning sand. So the pad's computer and mechanics are tested at extreme temperatures. The parafoil lines are connected to the AGU, and under simulated flight conditions, the steering mechanism is stressed to its limits. When it's passed the test, it's ready to be connected to the parachute. The parafoil is what makes the Sherpa fly. It's made from double layers of super strong parachute material called ripstop nylon. Once it's sewn together, every centimeter of the material is checked. Even the tiniest nick could shear it and bring a huge payload crashing down. When the space between the two layers of chute material fills with air, the parafoil becomes a rigid rectangle, like the aerodynamic wing of an airplane. A Sherpa can have up to 100 suspension lines made of very strong nylon, which is built to hold 10 times the weight of their designated payload. Once the lines have been methodically organized and laid out, the chute is packed into a bag. 2004 was the first time a GPS-guided PADS was used. A U.S. headquarters in western Iraq that was home to a hospital and Marine garrison was at risk of heavy insurgent attack. The only way to get the much-needed supplies was from the air. Deployed from high above enemy detection, the newly developed PADS floated downward and steered itself to the correct coordinates. The food and medical supplies landed safely in the camp. The final step is to integrate the guidance unit and the parafoil. The PADS has the brawn to deliver 4,500 kilo care packages to their destination and the brains to get there on its own. Coming up on Battle Factory, the boots that form a soldier's footsteps, and the world's most popular pistol. When these strips of leather are cut and cobbled together, they'll march a Marine through a life of service. The Army boot is a symbol of military life that takes the soldier from the parade ground to the battlefield, but they aren't all created equal. The Danner rugged all-terrain boot is built to keep the U.S. Marine warm, dry, and protected, whether he's trudging through a desert or slogging through swamp. But it's been a long haul getting here. The trench boot took its first steps during World War I in the cold, wet mud of Europe's Western Front. Made from rough-cut leather with hobnail soles for additional traction, the boots were coated with wax dubbin to waterproof them against the persistent damp and the threat of trench foot, a disease that caused a soldier's feet to literally rot in their boots. But the coating wasn't enough, and 75,000 troops succumbed to trench foot. As military theaters changed, design of the military boot had to evolve along with it. The Danner all-terrain boot breaks down into the liner, the sole, and the exterior. The first step is to check the leather for quality and strength. Then the hides go to the leather cutting station. Steel dies cut out the patterns that will form the outside of the boots. The leather is then stamped with the official insignia of the United States Marine Corps. An automated sewing machine double stitches the boot's leather quarter panel with extremely strong nylon thread. Then the rest of the pattern is hand sewn to complete the side panel, which will keep the ankle dry and protected. 12 eyelets are punched out for laces, and then the side panel of the boot is sewn together. Once the excess leather is trimmed, the exterior of the boot is complete. Using dies that look a little like Christmas stockings, the boot liner is cut out of waterproof, breathable Gore-Tex. The pleated halves are stitched together using a surging stitch that can easily accommodate the curved shape of the liner. The booties are then inflated with air and dunked into a water tank to check for holes. Bubbles indicate a leak, which means they are either repaired or thrown away. These Gore-Tex liners ensure that the boots can tramp through ankle-deep water without getting the soldier's feet wet, making the boots 100% waterproof. The boot is ready to be put together. First, hooks are added for speed laces, just like on ice skates. The lining is stretched into shape on a plastic foot mold. A felt insole board is coated with glue and pressed onto the bottom of the lining. The top layer of the boot is glued on, and the leather is stretched right over the toe. The boots and rubber sole are heated to over 90 degrees Celsius to activate the adhesive. A tech clamps the boot and sole together to complete the watertight seal. First, they test the sole's bond to the boot bottom. It takes almost 115 kilos of force before the sole gives way. The laces and eyelets are jerked around over 15,000 times and still refuse to stretch or tear. Then the boots are dunked in water and flexed 100,000 times to simulate a tour in swampy terrain. Life is tough enough for a Marine without worrying about what's underfoot. The right pair of boots isn't just part of the uniform. They're as critical to a soldier's survival as their weapon. Coming up on Battle Factory, a straight shooter that aims for accuracy. These bits of steel and spring and coated plastic will pack into a pistol that's one of the most popular sidearms ever produced. Designed in the Czech Republic, the CZ75 9mm pistol was first designed in 1975 behind the Iron Curtain. Its firepower and accuracy became legendary and has since been imitated by manufacturers around the world. Today, the CZ75 is the default sidearm for a long list of police and military forces. The pistol breaks down into 4 parts: the frame, the recoil spring, the barrel, and the slide. Every time the pistol is fired, recoil slams the slide back and pops out the spent shell. Then a spring bounces the slide forward, chambering a new bullet as it returns to firing position. The slide starts out as a piece of raw steel. A robotic arm grabs it and puts it into a computer-controlled cutting machine. The machine then carves out the basic shape. Automatically selecting from a series of cutting tools and drills, the machine further refines the slide, rounding the edges and cutting out an ejector hole to jettison the spent cartridges. Every member of the U.S. Special Forces, like the legendary Delta Force, is armed with a pistol. When a Black Hawk helicopter was shot down in Mogadishu, Somalia, 2 Special Forces snipers insisted on being airdropped into the fray in order to defend the wounded crew under siege by a mob of Somalian insurgents. Armed with only their sniper rifles and pistols, they established a perimeter to protect the wounded crew. The first soldier was killed, and the second stepped directly into the line of fire, holding them off with just his pistol until the very end. For the first time since the Vietnam War, both brave soldiers were posthumously awarded the Medal of Honor. The barrels of the CZ75 arrive coated in rust. They're actually left outside during the changing seasons to be weather cured, which toughens the metal, a CZ family recipe. The barrel is made from a special alloyed steel, heat treated for hardness. Holes are bored through the center, 4 barrels at a time. Then the rusty outer bark is scraped off. The barrels are placed in a cold hammer forge. 4 hammers pound on the barrel at 1,000 hits per minute with 10 tons of pressure to stretch and toughen the steel. During this hammering process, a spiral-shaped tool forms corkscrew grooves on the inside walls, called rifling. When the bullet is fired, the rifling causes it to spin, which makes it fly straight and aim true. Then the rifling is inspected and the interior of the barrel is cleaned. The frame is made from a super-strength polymer reinforced with fiberglass. The spring absorbs the energy of the recoil and protects the frame from the impact of the slide. Every time the pistol is fired, the recoil sends the slide back into firing position, chambering a new round as it goes. Finally, the slide and barrel are joined with the frame. The gun is complete and ready for testing. Every CZ pistol is strong enough to be dropped from 4 meters with a round in the chamber onto a concrete surface. It will hold together, and the coated polymer frame won't crack under impact. Finally, the gun is loaded up and lit up at the firing range. Since its inception in 1975, there have been literally thousands of imitators of the CZ handgun. But whether it's on the firing range or the combat zone, when you need to give it your best shot, you want to reach for the real thing. When this construction of cogs, cables, and computer software hits the air, it'll become a flying eye in the sky and a high-tech bird of prey. UAV stands for Unmanned Aerial Vehicle, but these remote-controlled flyers, used for long-range reconnaissance and armed combat, are better known as drones. They come small enough to fit into a backpack or scale right up to a full-size fighter jet. It can outfly manned aircraft, staying aloft for over 24 hours at a time, often controlled via satellite link from a world away. The ING Robotic Aviation Responder is a surveillance drone that can reach speeds of 70 kilometers per hour. Weighing in at 45 kilograms, the $80,000 Helidrone is stable in extreme weather conditions and 60-kilometer winds. The Helidrone is currently deployed to East Africa, where the military use it to monitor border incursions. The Helidrone breaks down into the motor, the drives, and the frame. The mini-copter is made on a frame of carbon fiber, which is 10 times tougher than steel. The rest of the body is composed of strong, lightweight fiberglass, which won't disrupt the radio frequency signals that control the drone. The main gear drives the aircraft's main rotor and tail. All teeth on the gears are manufactured on a diagonal instead of straight up and down. This minimizes noise and vibration throughout the frame, which maximizes stability and stealth. Just like a full-sized helicopter, the drone is based on angled elements that provide lift and prevent the aircraft from spinning out of control. There are 2 drive systems, one in the main body of the frame and one in the tail. This 2-way drive helps to stabilize the drone so it doesn't spin and helps with the yaw, or left and right turns. The drives are made of CNC machined aluminum. First, the tail drive is assembled. Next, the main drive is constructed. The main drive is responsible for the lift of the drone. Its curved holders steady the aircraft and minimize spin. Surveillance drones were first used extensively during the Vietnam War. Dubbed Fire Bees, they were equipped with conventional cameras and ran reconnaissance missions. Not much change for UAVs for 20 years, until drones were able to see details from half a kilometer up and transmit those images in real time. And the sound of a drone often meant an attack was going to follow. So, in February 1991, after a U.S. battleship had devastated the Iraqi defenses of Failaka Island near Kuwait City, the Navy sent an unarmed drone at low altitude over the island. When locals heard the drone's signature sound, they figured the low-flying aircraft was about to direct another precision strike. The troops started surrendering to the drone's tiny camera. It was the first time in history that people surrendered to a robot. Assembly begins with the landing gear. The lower landing portion is made of lightweight aluminum. The raised legs allow for 8 inches of clearance for mounting cameras and large sensors. The copter is wired and the onboard computer and power source are installed. The 500-watt battery-powered motor will reach speeds of 70 clicks and run for about 40 minutes without a recharge. Finally, the propeller blades are inserted into the main and tail drives. The responder is made to carry a DSLR camera, which takes super high-resolution stills and video from as high as 275 meters up. Top priority for the drone's test flight is to make sure the UAV is vibration-free. Even the slightest rattle makes for a bumpy ride, a drained battery, and blurry images. Drones are on the rise. Whether it's deployed for high-altitude surveillance or targeted air assault, the drone is a powerful and controversial combination of human skill and robotic technology, and a long-range look at the future of warfare. Coming up on Battle Factory, a shock-proof, leak-proof carrier you can drop out of the sky, and a DIY solution to surviving in the woods. These granules of lightweight plastic will be melted and molded into a hard-shell, waterproof case that can be an emergency ward in a box. Until the early 1960s, military equipment and supplies were packaged and transported in wooden shipping crates. They were heavy and had to be pried open with crowbars, and once unloaded, they were trashed. These days, the shipping case is made from composite plastic. Lighter and more rugged than wood, the case can be clean enough to carry medical supplies and tough enough to drop out of a plane. They seal tight to keep out water, weather, and sand, while maintaining a constant atmosphere and sterile environment inside. The ECS case breaks down into the hardware and the body. Grains of sand-colored polyethylene are weighed out, then shoveled into a mold. Then a lid is put on, and it's secured to a robotic arm. First, the mold is rotated so the polyethylene grains inside are distributed evenly. Next, the arm moves into a large oven that heats the poly to 300 degrees Celsius for 20 minutes. Once heated, the granules of poly melt together to form a solid plastic that conforms to the shape of the mold. Then, it's shifted to a cooling bay, where an industrial fan dries it to a hard finish. Still hot to the touch, the cases are pulled from the mold. During molding, solid foam is placed inside the shell. As it cools, the case shrinks approximately 6 millimeters, and the foam inserts help maintain its shape. A blanket prevents it from cooling too quickly. Once it's cooled down, the foam inserts are punched out. After a further half an hour, the excess plastic edging, called the return cap, is shaved off. A blowtorch smooths out the edges, and a plastic soldering iron seals any spots where the shaving created holes. The surface is buffed, and an angle blade X-Acto knife trims off the remaining plastic shards. Finally, a flattening agent is sprayed to remove the unwanted reflective gloss left by the blowtorch. During the Korean War, mobile Army surgical hospitals, or MASH units, were set up as close to the front lines as possible, while still trying to keep the doctors out of harm's way. The result is that many people died on stretchers and in jeeps on the way to get help. Now, cases like the ECS case mean that a hospital can literally be dropped from the sky to the front lines. Sterile, protected medical gear survives the journey and can mean the difference between life and death. First, small metal cables called lanyards are clipped on. These serve as the lid's hinges. Next, a hole is routed and trimmed for the pressure relief valve. This helps to depressurize the case during air transport. Then, the case is handed off to a second workspace where the latches are mounted. Now that the case is assembled, glue is applied to the slot along the edge and fitted with waterproof rubber stripping. Then, the case is submerged to make sure the seal holds. Once it passes the water test, the case is packaged up and prepped for shipping out. No matter what the cargo, at this plant, there's a strong case to be made for it. Coming up on Battle Factory, a how-to guide to putting a roof over your head, and a half-ton pickup that morphs into a super truck. For a downed pilot or a soldier caught in hostile territory, the key to survival is rest and shelter. Elite forces have created training exercises that teach the soldier to build an A-frame shelter that both protects him from the elements and hides him from the enemy. The A-frame shelter breaks down into the frame, the roof, and the camouflage. But before starting on construction, you've got to find the right location. When scouting a location to build a shelter, look for natural camouflage, like a clearing surrounded by a dense thicket of trees, with plenty of fallen branches, twigs, and leaves to use as construction material. The ground should be level so the structure will be stable, and so water will drain away from the shelter. The optimal site would be hidden from view, but still have access to water and food in the form of edible vegetation like berries or mushrooms, and bugs for a crunchy protein snack. The first thing to consider is the size of the shelter. It's got to be long enough to provide cover from head to toe. An operative will lie down to mark the length with sticks. Bedding comes first. The shelter is built around it, so the frame isn't toppled over while trying to get the bedding in. Tree bark and fir branches create a soft, comfortable surface that separates the body from the ground to keep cold and damp out. More body heat is lost to the ground than to open air. The A-frame is made of 3 strong branches. The arms, which are made of 2 pieces of equal length, support a spine called a center pole, which runs lengthwise from the arms down to the ground. If they can be found, arms with forks at one end are best for supporting the center pole. The length of the arms determines the height of the shelter. Lower shelters do a better job of retaining body heat, but limit maneuverability inside. Flexible cedar branches act as a natural twine to tie the arms together. On June 2nd, 1995, fighter pilot Scott O'Grady was shot down over Bosnia, forcing him to parachute into hostile and desolate forest. Without food or water, O'Grady knew he had to keep out of sight and stay alive until help arrived. He'd have to rely on his survival training. By day, he slept in shelters built with whatever he could find on the forest floor. He traveled by night to avoid detection. Subsisting on plants, bugs, and rainwater he collected in a sponge, O'Grady managed to survive and evade capture for 6 nights before being rescued by the Marines. First, the woods are foraged to collect branches of increasing height to line up with the angle of the central pole. If need be, the branches can be snapped into size or cut with a pocket knife. The roof is constructed by leaning branches against the central pole a few inches apart in order to form slats. Once the slats are complete, young leafy branches are threaded through and piled on to create a weatherproof thatched roof. This thatched roof will keep out wind, rain, and snow while trapping body heat inside the shelter. For a soldier stuck behind enemy lines, survival also means avoiding discovery and capture. So the shelter is draped in natural camouflage made of fallen leaves. It might not be the best night of sleep he's ever going to get, but the survival shelter means the soldier can stay warm, dry, and alive until help arrives. Coming up on Battle Factory, a bulletproof troop carrier that keeps rolling under fire. Take a standard pickup, strip it down, and build it up with ballistic steel, and an ordinary truck becomes a bulletproof fortress on wheels. The Incas Armored Personnel Carrier is speedy, agile, and bulletproof. It can transport up to 10 troops or police in and out of hostile territory at 90 kilometers per hour and keep them safe even under high-caliber weapons assault. World War I saw the advent of the Armored Personnel Carrier, the Mark IX, which was first deployed to the Western Front to safely carry infantry accompanying tanks past enemy lines. Now troops could be transported in larger numbers and dropped directly into combat. While production started in September 1917, only 3 of the Mark IXs were made in time before the war ended in 1918. Even though there were only a small number of APCs produced, they forever changed the way battles would be fought. The Incas Armored Personnel Carrier breaks down into the frame, the chassis, and the armor. The Incas Armored Personnel Carrier starts out as a stock Ford F-550 Super Duty truck. The transformation begins by stripping the truck, tearing it down until all that's left is the chassis, a bare metal frame, and the engine sitting on 4 wheels. Now, it's ready to be rebuilt from the ground up. The chassis is reinforced with mild steel, so it can withstand hard riding without cracking. And the brakes and suspensions are tricked out so they can handle heavy armor over rough terrain. The next step is to add the armor, which creates a virtually impenetrable shell able to withstand explosions and enemy assault. But before it can be added, the ballistic steel, called B6, has to be tested. 1 sample square from each batch is pulled, and 3 rounds are fired into the same spot. If none of the bullets pass through the steel, it's considered ready for use. If the metal fails the test, the entire roll is trashed. The bulletproof metal is put into production, and the armor plating can begin. Shapes are carved out with a laser, including the windows and gun turrets. Next, the armor is bent into shape on a 10-ton press. Ballistic steel is also used to fully encase the vehicle's engine in a bulletproof cage so it can keep running under fire. By the onset of the Second World War, both sides realized the necessity of mobile command and control in wartime. As a result, APCs were produced and employed by both the Axis and the Allies in much larger numbers than before. And the carriers evolved from simple armored cars to the ultimate in sophisticated engineering and highly effective tools of war. Today, they're an indispensable asset for armies around the world. The APC's frame is made from mild steel. Its low carbon content means the metal will flex instead of cracking under the impact of a bumpy ride or bomb attack. The steel floor fortifies the chassis against landmines. The outer frame is assembled, lowered onto the chassis, and welded together. A layer of foam insulation is sandwiched between the steel plates to protect the passengers from harsh weather, as well as providing another anti-ballistic layer. The B6 ballistic metal is then welded to the inside of the hull, making it completely bulletproof. A projectile would need to puncture the mild steel, pass through the foam insulation, and penetrate the ballistic steel in order to hit and harm the vehicle's occupants. Nearly impossible. Once the truck has been coated with a textured paint that forms an anti-reflective skin, work is done on installing the bulletproof windows, the seats, and the dashboard. After hundreds of work hours, the armored personnel vehicle rolls off the line for a test drive, pushing it to the speed limit on the highway, then knocking it around to make sure it's off-road ready. Converting a stock pickup into an armored vehicle is like turning a mortal into a superhero. And when the transformation is complete, this monster truck is unstoppable. When these tiny tools are machined and joined together, they will make up the ultimate mini multitasker. Since its invention over a century ago, the iconic Swiss Army knife has evolved into a pocket-sized hardware store with fold-out features that include everything from tweezers to a wood saw. In 1891, in his cutlery shop in Eibach, Switzerland, inventor Karl Elsner came up with a multi-tool which incorporated a knife, can opener, and screwdriver in one compact body, the soldier's knife, and soon became standard issue to the Swiss Army. Today, the Swiss Army knife is used by millions of soldiers and civilians alike for everything from chopping firewood to building a spear. The Swiss Army knife breaks down into three parts: the case, the dividers, and the tools. All the steel tools are made with 13% chrome to make them rust resistant. Before construction begins, the steel sheets are checked for consistency. A spectral analyzer measures the purity of the metal. Spools of 3mm thick steel are transferred to the punch press room. 20 computer-controlled presses punch through the steel with 40 tons of force to cut out the Swiss Army knife's legendary blade. Each strip of steel will produce 30,000 knives. Next, the bottle openers, can openers, and the rest of the Swiss Army knife's many gadgets are punched out. The classic model contains 7 tools, including the penknife and scissors. But some knives, like the Swiss Champ XXLT, have 70 gadgets, including pliers, a magnifying glass, and a ballpoint pen. The blades are placed in huge vibrating machines filled with stones and rubber chunks, which grind against the blades to deburr or smooth the edges. Then the blades stick to a magnetic wheel, which picks them up and drops them onto a conveyor belt. They're deposited into a rotating tank full of sand, where they're dried and degreased. The excess parts are shaken loose in a jitter machine. The knives and other pieces are heated and then rapidly cooled. This alters their molecular structure and hardens the metal. Next, the parts are transferred to the automatic shape machine. The grooves, angles, and inserts are machined into the metal blade and can opener, which enables the user to grasp the tool between their fingers and pull it out of the case. In 1995, during his first mission into space, Canadian astronaut Chris Hadfield used his standard-issue Swiss Army knife to dock the space shuttle Atlantis to the Russian space station Mir. The cosmonauts had secured the hatch with a tough triple-knotted strapping material, and Hadfield simply couldn't untie it to open the door. Unclasping the blade on his Swiss Army knife, he was able to cut the strapping get the door open, and make history. All the parts are collected and itemized in a sorting room before they're shipped off for assembly. Pins are pressed into the case walls, which hold the entire mechanism together. Each item is placed in layers by hand. Then a machine stamps them into place. A bushing is placed in between layers so that each tool unclasps smoothly without getting stuck on its neighbor. Then the cover is press-fit on, and the little plastic toothpick is slid into its sheath. Before they leave the plant, every function on the knife is checked by hand. The Swiss Army knife is complete. Whatever the add-on, the Swiss Army knife has already earned its reputation as a legendary toolkit and a survival kit you can hold in the palm of your hand. Coming up on Battle Factory, taking aim with laser-sharp accuracy, and what to wear to the front lines. When power runs through this diode and lens, it will project a laser beam that pinpoints a target with total accuracy and plants a red dot right on the bullseye. The Crimson Trace MVF 600 red dot laser sight fits on the rail of a gun, and with its built-in flashlight provides precision targeting in any environment. Red dot laser sights were invented in 1975, but they weren't adapted by the US military until the year 2000. Today, the laser sight is an integral part of the soldier's kit, sharpening aim and enhancing targeting, especially for nighttime operations. The laser sight breaks down into three main parts: the flashlight, the tang, and the laser. The laser consists of a diode, which is an electro-optic, like the little filament inside of a light bulb, and a precision lens. In order to make the laser work, two tail wires need to be attached to the end of the diode, and the lens placed on top to focus the beam. First, the diodes are steadied on a fixture, and then the brass tips are snipped off. Next, the wires are dipped in an acid solution, then soldered to the diode tip. Now wired for power, another technician presses the diode's tail post firmly in place with a coating of epoxy. The bond has to be tight for the laser to project a perfectly straight beam. Then it's left to dry for 24 hours. The lens is dropped into the lens holder. The cap goes over the holder, and the lens system is pressed fit together. The lens system amplifies and focuses the laser beam, which can project onto an object up to 230 meters away. Pulling off a covert operation takes exhaustive training and razor-sharp aim. An elite team might take days closing in on their objective, and then suddenly storm their way past a heavily guarded perimeter. With the laser sight pinpointing their target, that red dot will be the last thing their targets ever see. The laser and flashlight sit on opposite sides of the sight's handle. First, the flashlight's electrical system is assembled, then capped inside the casing. Then, the laser's diode and lens are fit together. Once connected, a tech calibrates the laser beam for sharpness and accuracy. The laser is then locked into its casing to complete construction. The tang contains the laser sight's power supply, housed inside the grip. Once the circuit board is programmed, It's installed alongside the batteries it controls into the handle. The tang attaches under the barrel of the weapon, doubling as a grip onto which the flashlight and laser are mounted. The on-off switch is right on the grip, so the shooter never has to take his hand off his weapon to activate the sight. The laser sight is calibrated to ensure total precision. The MVF-600 is ready for action. On the firing range, the laser sight is tested for accuracy. The beam aims for a target 30 meters away, focusing the red dot at its center. Bullseye. In the real world and combat zone, the MVF-600 will do what it's designed to do with lethal precision. Guide a bullet so it lands right on the red dot. Coming up on Battle Factory. A suit of armor for the modern-day warrior. And looking down the barrel of a submachine gun. These bolts of bulletproof fabric will soon become wearable protection and a soldier's last line of defense. In the past, body armor tended to be clunky, cumbersome, and restrictive. Today, it's built for maximum protection and maximum mobility. Fenix combat body armor owes much of its strength to a lightweight synthetic ballistic material called Armoured. Comprised of 82 different pieces, the Fenix body armor is made up of the armored plating and the fabric. Rolls of camouflage fabric are laid out onto a table. Templates of the 60 shapes that make up the vest are laid over the material, traced and cut. A layer of 3D shock protection netting lines the inside of the vest, absorbing the impact of an explosive shock wave or bullet to minimize injury. Camouflage fabric pouches are sewn into the netting that will hold padding and armor. The basic profile is then sewn together to form the front and back of the vest. Heavy nylon strips are sewn into the vest to hold the surface components of the armor in place. Layers of Armoured form the soft ballistic protection packets. They're placed in waterproof bags and sealed with an ultrasonic welder before they're inserted into the vest. This process is vital, as any water or moisture in the Armoured will compromise its bulletproof nature and make it act more like a lubricant, actually helping the bullet to penetrate the wearer. In a Taliban compound in Afghanistan in February 2008, Royal Marine Corporal Matthew Croucher was patrolling with his crew when he hit a tripwire tied to a grenade. With only seconds to react, Croucher threw his backpack onto the grenade and dove onto it, hoping his sacrifice would save the rest of his team. While the explosion tore up his gear, his body armor absorbed enough of the impact to save every member of his unit, himself included. Croucher was awarded the George Cross for gallantry. The rigid armor is made from plates of strong, lightweight PVC. The smaller segments are die-punched by machine, but larger pieces, like the backplate, are traced, cut, then punched out by hand. Holes are punched out of the PVC plates to lighten the armor. The plates are then sewn into the pouches in the front, back, shoulders, and around the waist. When the vest is tightened, 35 kilos worth of armor plating is spread evenly around the body, taking the stress off the shoulders. Now, the body armor is ready to be assembled. The packets of Armoured are inserted into the camouflage fabric, and the 3D shock protection pouches are sealed with Velcro. An additional layer of heavy ballistic material is inserted into the body of the vest. The front and back pieces of the vest are attached to a quick-release system so they can be ripped off to alleviate weight or treat an injury. Then the groin, shoulder, neck, and other padding is attached to the main body. The completed armor is ready for testing. On the firing range, the body armor is draped over a thick block of putty to simulate a human body. First, it takes rounds from a semi-automatic 9mm. Then the armor is checked to see where the bullets might have penetrated. Marks in the putty would be wounds on the wearer. Then the process is repeated with a submachine gun. If the armor survives the test, it will be shipped out to Special Forces units, who will custom kit them to their personal specs when they wear them in the field. And the next time bullets are fired at this armor, it will be protecting flesh and blood. Body armor won't make the wearer invulnerable, but this protective gear can get in the way of a bullet and keep a soldier alive. Coming up on Battle Factory. A single round or full-on automatic, it's the right weapon for any operation. When this steel pipe is drilled and honed, it'll become the barrel end of a weapon that's compact, versatile, and deadly as a scorpion. The Scorpion submachine gun is lighter than a rifle and more versatile than a handgun. Fast loading with a fold-out stock, it can fire single shots, 3-round bursts, or empty its magazine in full auto. Accurate to 200 meters, the Scorpion is the weapon of choice for many military and security forces around the world. And the Scorpion machine gun's ability to shoot with precision is built right into the barrel. The steel used to make the Scorpion's barrel is first left to cure outside the plant. Weathering the rain, heat, and changing temperatures might coat the metal with rust, but it also makes it more durable. First, the barrel is precision drilled to create a hollow running the length of the cylinder. Next, the opening is bored out in 115mm sections. The barrel spins on a lathe to scrape off the rust and smooth out the surface. In a hammer forge, 4 synchronized hammers pummel at the steel 1,000 times per minute with 45 tons of force, extending the length of the barrel and etching out corkscrew grooves on the inner wall. These unique grooves, or rifling, cause the bullets to spin so they fly straight and true. Then, the barrel is cut to length. Finally, a technician inspects the barrel's interior, cleaning out any debris and checking the rifling that makes up this Scorpion's distinctive fingerprint. Any flaw in the barrel could send a bullet way off its mark. The trigger is cut to spec inside a computer-controlled cutting machine. Small components that make up the submachine gun's action, including the slide stop, trigger, and dynamic bolt, are baked in a very hot kiln to harden and toughen the metal. On April 30th, 1980, 6 armed men stormed the Iranian embassy in London, taking 26 hostages and demanding passage out of England and the release of their imprisoned brethren. For days, British police stalled, managing to gain the release of 5 hostages without giving in to terrorist demands. In frustration, the terrorists executed a hostage. With lightning force, the British Special Air Services, armed with submachine guns and stun grenades, stormed the embassy, killing 5 of the 6 terrorists and rescuing all but 1 of the hostages. The SAS solidified their reputation in the most successful rescue op of all time. All in all, it takes about 25 minutes to assemble the gun. Each part must fit precisely to within a millimeter's tolerance. The barrel is attached to the body of the gun. Next, the trigger assembly and slide are inserted into the stock. The Scorpion submachine gun is known as the gun that'll shoot under any condition. To make sure it lives up to its rep, testing goes to extremes. First, the gun fires 2 overpressure rounds, 20 to 30% more powerful than a typical round, to ensure the strength of the gun. Then, the gun is subjected to a 5-round precision test, the results of which are measured by a computer. The Scorpion is built to withstand being dropped from a height without shattering. It can also be submerged until water fills the gun. Once it's completely soaked, rounds can still be fired in full automatic mode. Even when the gun is dumped into thick bogs of mud and coated, it continues to fire. The Scorpion submachine gun combines the best of a full-scale automatic rifle and a nimble handgun. And like its namesake, it's got survival skills and a killer instinct.